Hello friends, today's question. A small sphere falls from rest in a viscous liquid. Due to friction, heat is produced. Find the relation between the rate of production of heat and radius of sphere at terminal velocity. So, it is given that there is a sphere which is falling through the viscous liquid, and there is a friction between the sphere and the viscous liquid, and that is going to produce the heat. So we have to find out the relationship between the radius of sphere, which is we suppose is given as small r, and the production of heat. So in this case, we have to remember that as the sphere start to fall with the terminal velocity, all the forces which are associated with that sphere is in equilibrium. Okay, so we are going to have obviously two forces. One will be the gravitational force that will be acting in downward direction, and another one will be acting in upward direction, that will be buoyancy force. So it means the terminal velocity is somewhat related with the drag, you can say drag force. So the net drag force will be equal to the net you can say equilibrium forces, and that equilibrium forces will be the combination of your gravitational force as well as buoyant force. So this is basic, and we are going to solve it, and we are going to get the relation from there. So we are going to start from that when a small sphere falls at its terminal velocity, which is suppose given as Vt in a viscous liquid, forces on it will be at equilibrium. Forces on it will reach equilibrium. So if the forces are in equilibrium, so because of that we can say this results in a constant speed of the sphere, and at that constant speed the gravitational force is balanced by the buoyant force and the drag forces. So you can say this results in constant speed at which the gravitational force is balanced by the buoyant and drag force. So we can draw you can say rough approximate diagram for these two statements. So this is the sphere, and it is moving in the downward direction with the velocity Vt. So obviously we are going to have in the downward direction there will be a gravitational force, and in the upward direction we are going to have two forces. One will be the buoyant force, let us call that as Fb, and another one will be drag force, let us call this as Fd. So upward we have Fb and we have Fd, and in the downward direction we are going to have gravitational force, let us call that Fg. So at equilibrium, all these forces will be equal to each other, we can say Fg, that a gravitational force will be equal to summation of the buoyant force as well as drag force. So gravitational force is given as Fg. So this is the basic relationship based on which we are going to drive the entire relation, you can say the relation between the terminal velocity and the radius. So let us start with the terminal velocity and the drag forces. Terminal velocity and drag force rather. So the drag force Fd at the terminal velocity is given by the Stokes law. So we can say that the drag force Fd on the sphere at terminal velocity, and the terminal velocity is given as Vt, and it is given by Stokes law, given by Stokes law. So it tells us that our force Fd, that's the drag force, is equal to 6 pi nu, and we have R multiplied by Vt. Okay. So here this nu is the viscosity of the liquid, and the small r is the radius of sphere, and Vt we already know is our terminal velocity. Let us, you can say, find out what will be the, or rather we can say that at terminal velocity the net force on the sphere will be equal to 0. So you can say at terminal velocity the net force on the sphere is 0. So it means we can write that the drag force which is of Fd balances the net downward force, balances the net downward force, and this net downward force is our gravitational force minus buoyant force. So in the form of the equation we can write it as that our Fd, which is our drag force, will be equal to, we have gravitational force Fg minus buoyant force, that is our Fb. So we substitute the, you can say, values of Fd. Fd was our 6 pi nu R multiplied by Vt, and Fg is our gravitational force, and that we can write as your rho s, which is the density of the sphere, minus, and we have rho liquid multiplied by V and G, and in this case our rho s is density of the sphere, is density of sphere, and rho f is the density of the fluid, density of fluid, and V is the volume of the sphere. V is the volume of sphere, and obviously that will be equal to 4 by 3 pi r cube, and G is our acceleration due to gravity. Acceleration due to gravity. So from this equation we can write from here that our Vt will be equal to rho s minus rho f divided by, this will be 6 pi nu r, and we substitute value of volume. Volume is our 4 by 3 pi r cube and multiply by G. So pi goes with pi, this cancel with this, we are left with square, and we can write this as 2 and this comes as 3. Yeah, so these are the only things which are going to cancel with each other. So we can write this as that our Vt, that our terminal velocity Vt will be equal to 2 by 3, and we have rho s minus rho f divided by nu, and this gives us G, and we have here r square. So this is the expression for our terminal velocity, but we are supposed to find out the rate of heat production. And rate of heat production, let us suppose if we denote it by P, then that P will be equal to the drag force and the velocity with which the that sphere is moving, which is the terminal velocity. So we can write here rate of heat production, rate of heat production. So rate of heat production, the rate of heat production, that is P, due to friction is given by the, you can say, power of the drag force is given by the power of the drag force, that is Fd multiplied by Vt, where Fd is our drag force and Vt is the terminal velocity. So from here we can write that our P is equal to Fd multiplied by Vt. We substitute value of Fd as well as Vt. Fd is our drag force, and that is our 6 pi nu r multiplied by Vt, and this is also further multiplied by Vt. So Vt becomes now Vt square. So we can write this as 6 pi nu r Vt square, and we substitute value of Vt from this equation. So we get this as 6 pi, we have nu r, and Vt was our 2 by 3, and rho s minus rho f upon nu, and this is G r square and whole square. So we just open this entire square thing. So we get this 6 pi nu r multiplied by 4 by 9, and this becomes rho s minus rho f whole square divided by nu square. This is G square, and this becomes R4. we are not interested in other things other than the square, you can say radius. So we have r1 here and r in this. So this we can write in terms of only r is our r5. Rest of the parameter doesn't matter here. So therefore we can say rate of heat production, rate of heat production is directly dependent upon the fifth power of the radius, and that was asked us the. So this is the relationship between the heat production and the radius of sphere. This is the relation between rate of heat production and radius of sphere, and radius of sphere. So this completes the question. Thank you.